Our next speaker is Ron Pepino. Ron was an undergraduate at UConn, University of Connecticut. He worked with Alex starting in 2003. He's now a PhD student at University of Colorado, Boulder, where he works with Murray Holland.
Thank you, Jim. So, as Jim said, I met Alex in 2003 through Robin Cote. I got an invitation to come up to ITAMP, originally for a 2-month internship. And that 2-month internship turned into a 3-month internship, turned into about a year plus that I spent there. And the research project that I worked on with Alex and Vasily was the solar wind charge exchange mechanism, which Vasily talked about yesterday. It was a great project, and as we saw yesterday, it was something that was in fact scientifically relevant, which, as the previous speaker mentioned, is somewhat hard to come up with a project that an undergrad, can find tractable and have it still be scientifically relevant. But it also was tractable, which was probably the greatest part of the whole thing, because it's important to inspire undergrads to continue to do scientific research. And as an undergrad, it's very easy to get discouraged if you start on a project and it flops on you very quickly. And so the end result was that I think we got at least 2 papers from that work. I gained an invaluable amount of research, scientific and professional experience and skills from Alex, and really, and for that I'm very grateful. And in all honesty, if I wasn't given this opportunity to come to ITAMP, I think that there's actually a pretty good chance that I wouldn't still be in science today. And so I thank you very much for the experience, Alex. That being said, as Vasily mentioned when he introduced me the last time I did an ITAMP talk last year, despite my simple success in astrophysics, I've abandoned the field entirely anyway, and I've gone on with Murray and have done something else. So today I'm here to tell you about that research, which the research program Murray and I call Atomtronics. Is it still okay if I step away from the mic, or is that okay? Okay, well, just let me know if you can't hear me, I guess. But in the end, the research project is called Atomtronics, and the idea is to create atom-optical analogs for basic electronic components and devices. And what we try to do is we take optical lattices and we try to configure them with the experimentally tunable parameters to get these optical lattices to mimic such things as diodes or transistors or what have you. And so I'll illustrate the analogy that we're trying to create here by comparing the Atomtronics equivalent of the simplest circuit you could imagine, which is just a battery connected to a wire which has some inherent resistance. So basically what we want to do is we want to replace the current carriers, the actual electrons, the bodies that transmit the current. We want to replace those with ultra-cold neutral atoms. The battery itself we will replace with 2 reservoirs of ultra-cold gas. And the electric potential difference, which is the mechanism that propels the electrons around the circuit, we're going to replace with a chemical potential difference. And so we'll take the 2 reservoirs and we'll tilt them such that we can spill atoms across the lattice. Then the wire, which is really just a metallic lattice, we're going to replace that, or the semiconductor lattices, with the optical lattice. And if you wanted to, be cute and stretch the analogy, you could come up with some kind of Ohm's law equivalent as well, which would probably be governed solely by the tunneling rate of the system. Anyway, so why do this? Because I don't know, it sounds a little hokey on the face of things, I think, but there is some fundamental physics involved in this. So as far as system reservoir interaction studies go, this is it's a very novel set. Generally, when people employ this mathematical technique known as the master equation in quantum optics, they're trying to include something like dissipation in what once was a closed quantum system. And in doing that, the reservoirs solely consist of photon baths. And so we're not using photon baths for the reservoirs. We actually have massive particles in the reservoirs, not photons. And so what that does is that introduces a chemical potential into the formalism. And if Juha is correct, I think this is really the first time that such a thing has been introduced into the master equation. But also, the other thing that comes in is the fact that we have these atoms, and it does take a certain finite amount of time for those atoms to enter the system. And so we actually have a non-zero correlation time that we have to deal with as well. Anyway, once this formalism is constructed, it lends itself very easily to the study of transport properties of optical lattices, which I think is really probably going to be the most important thing that comes out of this research. Now, the condensed matter guys have their own way of doing transport property studies, but effectively, Murray and I are developing the quantum optical approach to doing this. And the last point, which I don't like to stress too strongly, but there's some idea that maybe these devices that I'm going to talk about can become candidates for quantum information devices, because in the end, it is an optical lattice, and the dynamics within the lattice are completely reversible, and that reversibility is needed in quantum information science. But again, I don't know how true that statement's going to end up being, and so I don't like to stress that very much. So in the end, this talk is going to be very qualitative, but I figured I would at least throw down the basic equation that we use. And so this is the master equation in what is a modified Born-Markov approximation. And so it is an equation for the system reduced density operator, which is sigma s. And if you have that, then you can find observables very easily by making the product of the reduced density matrix with the observable and then just taking the trace. So this is the equation of motion for the reduced system density operator. So we have that here. We have the reduced reservoir operator here. And then you have the Liouville operator, which is defined as just the commutator of the system Hamiltonian here. And then you have two Liouville operators, so it's a double commutator with the interaction Hamiltonian. And this eta here is our addition, which basically takes into account the higher order effects of the interaction. And so it's in a way it's an ansatz of the memory kernel and takes us a bit beyond the typical Born part of the approximation. And so what eta ends up being, 1 over eta, is basically our model for the finite correlation time for these interactions. So there's many ways you can do this. You can have your system, the atoms that you choose, you could have them be bosons or fermions. You could have them be atoms, or you could have them be molecules. Given a specific set of atoms, you can have a couple different situations. And these situations we've actually looked at extensively this last year. And so we've considered 3 different models for the reservoirs, one being bosons in the strongly interacting limit, where we say that the bosons are interacting so strongly that they cannot settle down into a Bose-Einstein condensate. And so one could imagine that maybe they have a 3D optical lattice where the on-site interaction energy prevents you from putting more than one atom in that site. And then we've investigated also the weakly coupling regime, where the bosons can form into a BEC, and then that BEC effectively coherently drives the optical lattice. And for reasons that I can get into later, we find that that actually does not make up a reservoir, basically because it interacts too slow with the system. And besides the bosons, you could do fermions as well, which we've extended our systems to cover fermions. But for the rest of this talk, I'll just assume the strongly interacting reservoir. And so, since the particles are bosons, we could use the Bose-Hubbard Hamiltonian, which this is the second quantized form, which I'm sure a lot of you are familiar with. So I don't need to dwell on it, but basically, so K, L, and M are the site indices. And so you have this external energy term here, which says, okay, we'll count the number of particles and assign the correct external energy to it. If you happen to put more than one particle on a given site, there is this interaction energy. There is an additional energy cost, which is taken care of in the second term. And then, of course, the tunneling rates are determined and limited by the overlap integral. And so the first device I was going to talk about was, and that we realized, was the Atomtronic Diode. And so how do you make a diode out of an optical lattice? Well, a diode is basically just a one-way avenue for current flow. And so we have these three parameters in the Bose-Hubbard-Hamiltonian, which are, for the most part, experimentally independently tunable. And so basically we wanted to augment them in such a way that we created this one-way flow of atoms across the lattice. So if the lattice is completely flat and symmetric, the current is symmetric. So if you swap the reservoirs, you'd see the same readout of the current. And I think that just makes sense from the geometry of the system. What we find is if we put like a step function increase in the external energy, we start to see an asymmetry in the current. And so we wanted to figure out how to optimize that. And so the other thing I wanted to note is that the important physics actually happens at the junction. And so if the diode itself was to consist of just these two sites, that would be qualitatively equivalent to if it was 4 or the 6 or the 8. The current pictures look the same. And so let's just focus on the two-site diode. So I have two claims on this slide. The first claim is that I can optimize the diode if I make the energy of the second site equal to that of the first, plus this additional on-site interaction energy. And if I do that, then the reverse bias is going to be if I try to flood atoms across from right to left, and the forward bias is going to be if I try to flood atoms from left to right. And we can understand why that is by looking at how the energies relate to each other in the Fock basis. And so here are just a bunch of cartoons of all the Fock states, and the height corresponds to the Fock energies. And so this would be the 0, 0 Fock state. This is the 1, 0 Fock state, and it has energy E1. This is the 0, 1 Fock state. It has energy E2. And here we're saying that E2 is equal to E1 plus U under this condition that I'm proposing is going to optimize the situation. But in the second particle manifold, we see that the 2, 0 Fock state is perfectly degenerate with the 1, 1 Fock state. And these two are separated in energy by the 0, 2 Fock state. And that's really what optimizes the device. And so the way we generally run these experiments is we start the situation with both reservoirs all the way down so that both reservoirs would take particles from the left and right lattice sites. And then if I start to increase the chemical potential on the right, eventually I'll be able to put in a single particle, which, because these guys are off resonant, there's a small chance that it can hop over, and if it does, it gets out, but pretty much nothing happens due to the off resonance between the states. Now, if I increase a little further, that off resonance just doubled, and so we're effectively locked into this state, and the system, and no current flows through the system. Resetting the experiment and going the other way, if I increase the potential to put in a particle on the left, then the same thing happens. It's the same off resonance, and so maybe you get a trickle of current, but nothing much. But then a very interesting thing happens if I increase the potential to put two particles in. And because the 2, 0 state is degenerate with the 1, 1, it's very easy for the system to flop and to put a particle on that right site. And when it does, the right reservoir can take it out and send it back down to the 1, 0 state, which is where you started. But since the job of the chemical potential on the left is to put in two particles to keep an occupancy of 2 on that site, it'll put that particle back in. And so you see that you've accessed a resonance cycle in which current can flow through that system. Similarly, if you're in the 1, 1 state, before the right reservoir removes the particle, the left reservoir can put another particle in. And again, you're separate from everyone else, and so you wait until the right reservoir takes you out, which drops you back down to where you started. And so there's another cycle in which current can be generated. And so here's a numerical plot of the 2-site diode. And if I did the 4-site diode, it would pretty much look identical. And so taking the reservoirs from the reverse bias and shifting them over and going to the forward bias, the current exactly turns on exactly at that resonance. Now from the explanation I gave, you might assume that, well, it should just go up in one step. So this graph here is just this expanded. And you see that it doesn't go up in one step. It actually kind of goes up in 2 steps. And the reason why it goes up in 2 steps is that the way the reservoirs talk to the system, it's not through the Fock basis of the system, it's through the eigenbasis. And when you diagonalize that Hamiltonian, you're going to get those energies are going to separate by a plus or minus j. And so we see that effective splitting is on the order of 2j. And this broadening of the tails is due to the fact that we do have this finite correlation time, which if you looked at Gardner and Zoller's book, you could relate that directly to thermalization. We doing okay? So the next device I wanted to mention that we've worked on was creating a transistor. And so basically what we wanted to do is we wanted to get current amplification and switching behavior as controlled by the base leg. So a transistor is a device with 3 legs, and so we're going to need at least 3 wells this time, and we're going to need 3 reservoirs. And once we realized that through these resonant arguments we can get a lot of mileage out of these resonant arguments, and we can create these other devices, we basically figured that if we make the site energies of the left and right wells equal and separate them from the middle well by a factor of the on-site interaction energy, we can get this degeneracy in the 2-particle manifold. And this does give us transistor action, because if the middle reservoir is fixed to have no particles in the system, and the right and the left reservoir is fixed to put in a single particle, and the right one is fixed to take everything out, pretty much all of the population stays here. This state is resonant with this, but you have to go through a second-order off-resonant process to get there. When you turn up the chemical potential in the middle to put on a single site, what can happen is you can go from the 0-1-0 state to the 1-1-0 state, and then the resonance can take you over to the 0-2-0 to the 0-1-1, and then you're out. And so you've essentially turned on this avalanche of current. Problem is that since the middle potential is set to have an occupancy of 1 particle on that site, if it sees 2, it can also take it out. But what you could do is at least theoretically, you have the right to make that coupling independent from the other couplings, and so you can just make it weaker and put a bias on the favored process. So here's the numerical data from that experiment, where we assume that the coupling in the middle is 10 times weaker than the coupling on the end. And so we have this finite, so this is the green curve here is the base current, and the blue curve here is the emitter current. And so we see that we actually do get a large amount of gain from this system, from this setup. Now, it would be nice if this tail was at 0, and it's not. And the reason why it's not, again, is because of that second-order off-resonant process. But by tuning the system, we can definitely drag that middle site level down further, and we can suppress that even more. So, oh yeah, and the gain is reasonably linear, which some people seem to like. So I just wanted to conclude by discussing one of the logic components that we have created. So a logic device is an input-output device that's characterized by what's known as a truth table. And so the device can have 2 legs or 3 legs on inputs and outputs or what have you. There's hundreds of different devices like this. So the gates that we've developed and that seem to work are the NOT gate, the AND gate, and the OR gate. And so I was just going to discuss what the AND gate was. And so what the AND gate is a 3-port device. You have 2 inputs and 1 output. And the way it works is you only receive a signal out if you're putting in signal in both A and B, which is what the table is implying. And so if you wanted to construct that, you could do it very easily by taking 2 transistors and connecting them in series, because if the middle legs are off, then no current goes through. So clearly nothing is going to come out unless both A and B are on. And so as a first stab at trying to create an Atomtronics logic element, we looked at this and we said, okay, well, let's just pretend that our silly little transistors actually are transistors. And so if we were going to connect them in series, the configuration would look something like this, where you had 1 transistor connected to the other, and and then you had your legs A and B, and you were trying to read current out. And I don't have the table of numbers. I think I do have it in an email somewhere. But we were actually able, in this setup, to recreate that logic table. And so that was pretty great. And so what we wanted to do next was increase the level of complexity up a step and try to work on digital logic to attempt to realize a pulse-driven device, like a flip-flop in an optical lattice. Mathematically, this is a very hard problem because everything that we've done so far is exact, and really because it is exact, and we're working in a Liouville space, which the problem scales terribly, and this is actually the biggest size of a problem that we can solve exactly in a three-state approximation. But if we're going to do the flip-flop, we're going to need at least one more site, and so we have to do something else. But also, this is it's going to be initial condition dependent behavior, and so we have to construct a whole new analysis because basically we do a steady state analysis on all of these devices. And also we wanted to extend the theory to larger systems and try to make composite devices using a technique like density matrix renormalization group, or what I think is probably going to end up being more appropriate is the time-evolved block decimation technique, which Anna Maria, I guess, has just arrived at JILA, and so I think she's going to help me out with that a little bit. So with that, I'd like to say thank you for your time, and we've developed all of these devices. I've only talked about a couple of them, but yeah. So I guess just to conclude, I should say that by solely manipulating the external energies of the optical lattice, we were able to reproduce the electronic behavior of the following devices. Sorry. Thank you very much.
Thanks, Ron.
Thank you.
Any questions for Ron? Bernard.
So we haven't attempted to do that yet, and I don't know if that's going to be possible, but I'm not really sure. It's definitely worth trying to try to. I think there's like an extra column in the truth table of a quantum information gate. That investigating that I think is next on the agenda.
Any other questions? Okay, let's thank Ron again.